Good luck.
Welcome to the Excell Battery Lithium Battery Safety Training. This presentation covers the basics of lithium battery safety, including actions to be followed if you experience a lithium battery incident. There are some documents attached to this course, which will be referred to at various times throughout this lesson. You can access these documents by clicking on the Resources tab in the upper right-hand corner at any time during this course. To navigate this course, you will notice some buttons at the bottom of your screen. The Next and Previous buttons on the right allow you to go forward or backward one slide at a time, but you will need to view each page before being allowed to move on. This course will advance automatically, but the Play button allows you to pause the presentation at any time. Let's begin. What are we covering? This presentation covers these areas: an overview of Excell Battery, how batteries work. To better understand lithium battery safety implications, it is important to understand the background of lithium battery chemistry and how a battery works. Safety and handling issues. We will cover actions and procedures that may cause a battery incident. Hazards of leaks and explosions. We will talk about what types of hazards may occur and the actions needed if a battery incident occurs. Incident response. We will cover what to do in the case of an incident and other important safety information. Who is Excell Battery? Excell Battery Corporation, based in the USA, and Excell Battery Company, based in Canada, are two separate companies, but combined are a major added value battery pack manufacturer in North America. We have been in business for over 29 years, and the two companies have locations in Calgary, Vancouver, Toronto, and Houston. Products offered by Excell Battery. Excell Battery assembles battery packs from every type of battery chemistry. These include lithium primary, which specifically are the type used in the majority of downhole, high-temperature applications; lithium rechargeable, which are most commonly lithium-ion batteries used in portable electronics, the same type used in your cell phones, laptops, tablets, etc. NiCad and nickel metal hydride, which are older rechargeable technologies but still finding a use in certain applications; lead acid, similar to car batteries; and alkaline batteries, such as Energizer and Duracell, which have some limited use in lower temperature downhole oil field applications. Oil market. Excell Battery specializes in the manufacture of high temperature capable downhole batteries. We do this mostly in two locations: Calgary, which is Excell Battery Company, and Houston, which is Excell Battery Corporation. These two locations are nearly alike, and we manufacture similar or the same products in both locations. We currently supply batteries for many downhole applications, including memory gauges and the drilling market, specifically MWD batteries. How batteries work. All battery types work similarly, and this discharge flow diagram explains the electron flow once a resistive load is attached to the circuit. Basically, once the resistive load is attached, ions will flow from the anode through the electrolyte and into the cathode, producing electricity. In the case of lithium thionyl chloride batteries, which is the basic chemistry used in the majority of downhole batteries, the anode consists of lithium metal, which is a very soft metal with an appearance like aluminum foil. The cathode is a carbon mixture, and the electrolyte is a liquid composed mostly of thionyl chloride. The separator is a thin paper with the consistency of tissue paper, which serves to separate the cathode and the anode. The anode and the cathode must not touch each other directly, and if they do, there would be an internal short circuit. There are three basic types of lithium thionyl chloride cell construction techniques. The different techniques determine the current capability of the cell, which can also affect the capacity and cost of the cell. Click on each thumbnail or the next button to see each individual picture. The first type is known as a bobbin cell. This diagram shows a top-down view of a bobbin cell, and this type basically consists of a cylinder of lithium, or anode, surrounding a cylinder of cathode, or carbon mixture. The current capability of a cell is determined by the common surface area between the anode and the cathode. In the case of the bobbin cell, the common surface area is the area between the two cylinders. A bobbin cell is also commonly known as a low-rate design. It is usually lower cost, it tends to be more rugged and capable of more shock and vibration abuse, but it has a very low current capability compared to other construction types. The dual anode or moderate rate design adds another layer of anode to the inside of the cathode, giving nearly twice the common surface area of a bobbin cell, which in turn gives the cell nearly twice the current capability of a bobbin cell. This is probably the most common cell construction technique used in downhole batteries. Moderate rate or dual anode cells have a medium cost point and, like a bobbin cell, are typically manufactured to withstand high amounts of shock and vibration. Spiral cells or high-rate design utilize a very long set of electrodes which are rolled into a jelly roll shape to give this cell a very high common surface area, which results in a very high current capability. These cells typically cost more, but in certain applications, the higher current capability is worth the extra cost. In downhole applications, recent improvements have made these cells rugged enough to withstand most downhole components of lithium thionyl chloride cells. This slide shows a side view or cutaway of a moderate rate cell. This view shows one other important feature common to all cell types, and this is the glass to metal GTM seal. The GTM seal serves to insulate the negative portion of the casing from the positive portion of the cell casing. In the case of the moderate rate cell, the anode or lithium touches the cell casing and the cell casing is negative as a result. The post sticking out of the glass to metal seal is connected to the cathode, which is the positive part of the cell. The glass to metal seal can potentially act as a pathway for electrolyte to leak out of the cell if the glass to metal seal is damaged. Lithium battery passivation. All lithium thionyl chloride batteries, the type described in this presentation, are affected by a phenomenon known as passivation. Passivation is formed as a result of the interaction between the lithium anode and the thionyl chloride electrolyte. This thin passivation layer is formed instantly when electrolyte is added to the cell, and it serves to protect the lithium from corrosion or self-discharge. In fact, the passivation layer is the reason the lithium thionyl chloride cells even exist. Without this layer, the cell would self-discharge at a very high rate or possibly explode. The attachment titled Electrochem Passivation of Primary Lithium Cells explains in more detail how passivation is formed and how users of lithium batteries can work with the passivation layer. The passivation layer thickens over time due to various other conditions, including prior discharge. The passivation layer acts as a high-resistance barrier between the anode and the cathode that needs to be broken down to allow efficient ion movement between the anode and the cathode. As it thickens and as the passivation layer resistance increases, the cell or battery voltage will initially drop to a very low level before recovering to a stable voltage. This is called voltage delay. The voltage recovery is a result of the passivation layer resistance breaking down, and this action is known as depassivation. Voltage delay may cause the cell or battery voltage to drop too low to power the device being powered by the battery. Depending on the user's discharge conditions, a depassivation step may be needed to remove some of the passivation to prevent voltage delay. After depassivation, the cell or battery should start at a higher voltage. The only acceptable and safe depassivation method is to place a resistive load on the battery or cell. No other method should be used. Heat, other than ambient temperature of a comfortable workplace, should never be used to depassivate cells or batteries. How safe are lithium batteries? This is a question we are asked all the time. Battery and cell manufacturing practices have improved over time, making the cells and batteries very safe to handle. When handled correctly, batteries are very safe. Battery incidents occur as a result of mishandling, abuse, or exposing to an over-temperature condition. However, due to the energy density inherent to lithium thionyl chloride batteries, potential hazards do exist if the batteries are mishandled. What safety procedures should be followed? The Electrochem safety and handling guidelines are available for download from the Excell Battery website. It is also attached as part of this presentation. The document covers in detail information shown in this presentation. The Excell Battery SDS, which is also available for download from the Excell Battery website, contains many important warnings and guidelines when handling lithium batteries. The SDS is attached to every box of batteries delivered to customers, and it is always available upon request. As the warning label says, any condition exposing batteries to a flame, high heat, short circuit, and recharging circuits should always be avoided. Common sense is an important element in the safety of lithium batteries. If you think you are doing something wrong, you probably are doing something wrong. Lithium thionyl chloride batteries do not explode or leak on their own. They must be abused in some way to cause these hazardous conditions. What are the safety implications of lithium batteries? As the slide shows, all hazards are associated with causing an over-temperature condition. If a cell or battery experiences an over-temperature condition, a leak or explosion may result. Some cell manufacturers will use the term vent when describing an explosion. This is not correct because high-temperature lithium thionyl chloride cells are not designed with vents. If the temperature of a cell is high enough, then the rapid pressure release is an explosion, not a venting. The warning label on cells and batteries must always be followed. The warning label will say, "Do not recharge, disassemble, overheat, incinerate, or expose contents to water." If any of these conditions are exceeded, then a leak or explosion may occur. What happens when the temperature rating is exceeded? All cells have a maximum temperature rating that is marked on the cell or battery pack. At temperatures above the temperature rating, the cell may leak electrolyte, which can be a hazardous situation in itself. Above the temperature rating of the cell, there is the melting temperature of the anode or lithium, which, if exceeded, will most likely result in an explosion. What is a battery leak? A battery leakage occurs due to a failure of the glass to metal seal, rim weld, or other breach of the cell casing. These types of failures occur due to a cell exceeding its temperature rating, which causes increased pressure on the inside of the cell casing. If a cell leaks, the primary hazards are a corrosive atmosphere, which will corrode electronics and metal surfaces, and an inhalation hazard that can be toxic to humans. Although an explosion has the added hazard of shrapnel, the corrosion of a leaking battery can be just as damaging to surrounding equipment as an explosion. This is a photograph of a lithium battery that had leaked inside a pressure housing while downhole. The corrosion of the thionyl chloride caused the appearance of the stainless steel casings as seen here. What are the causes of a battery leak? The most common reason for a battery leak is an over-temperature condition, higher than the temperature rating of the cell, but lower than the anode melting temperature. As mentioned previously, the increased pressure from the electrolyte may cause the glass to metal seal to break, allowing electrolyte to leak out. Other less common causes of a leak are a defect in the glass to metal seal, which is very rare, or external corrosion from an outside source. In the latter case, external corrosion can eat through the stainless steel, thereby allowing electrolyte to leak out of the can. What is a cell explosion? A cell explodes when the temperature of the lithium melting temperature is exceeded and the lithium becomes molten. At that point, the molten lithium will react violently with the electrolyte, causing a detonation. This is a tremendously high release of pressure, causing the battery and surrounding battery housing to break into many parts. Shrapnel from the battery parts flying through the air is an extreme danger that can cause damage, injury, or even death. Other than shrapnel, the hazards are a corrosive and toxic atmosphere, which are the same as a leaking battery. These pictures show the result of a cell explosion. The first two are lithium cells, and the last one is a lead acid. Click on each thumbnail or the next button to see each individual picture. You may also click on the magnifying glass to see a larger view of each one. Clicking again on the picture will exit the magnification view. This photograph is a common automotive type battery, and it is an illustration that any type of battery can be a hazard if mishandled. Batteries are energy storage devices, and if mishandled, the potential for hazardous problems exists. What are the causes of a battery explosion? All of the causes listed here result in an over-temperature condition. Basically, all will cause the lithium anode to become molten, and an explosion may occur. Click on the Next button to advance through the list. The first is when the temperature rating of the cell is exceeded. If the temperature is high enough to cause the lithium to melt, then an explosion most likely will occur. Short-circuiting a cell at high temperatures will cause rapid buildup of the internal cell temperature. If the ambient temperature is high enough, the internal buildup of temperature from a short circuit can cause the lithium to melt. Most batteries have built-in fuse protection, but if an internal short circuit develops, such as from abuse due to excessive vibration or shock, The fuse protection may not be helpful in preventing internal heat buildup. Fuses are only effective for external short circuits. Charging currents applied to lithium thionyl chloride cells may result in internal lithium anode heating, causing an overtemperature condition resulting in an anode meltdown. An explosion will result. In many cases, lithium batteries are protected with blocking diodes to prevent charging currents from reaching the cells. If high-voltage series strings of cells are connected to a nearly depleted cell, then the cell might be over-discharged, or cell reversal. This can also result in internal heating to the point of anode melting. Nearly all large lithium batteries contain cells with parallel diodes, thereby preventing over-discharge of individual cells in a series string. Excessively high vibration or shock may cause an internal short circuit, and if combined with higher than room temperature condition, may allow the anode to exceed its melting temperature. In many cases, this could be due to the separator paper tearing and allowing direct contact between the anode and the cathode. This is an internal short circuit, and it may raise the anode temperature over the melting temperature. If a cell is crushed, then internal components may tear the separator paper, causing an internal short circuit that may result in an explosion.
These two pictures show a couple of examples of cells that have seen high pressure inside a pressure housing. In both cases, the cells were crushed by pressure, but an explosion did not result. It is possible that subsequent use of these cells may result in an explosion if used downhole again. These photos serve as an example to suggest that users inspect the batteries after use if there is any indication that a pressure leak occurred in the battery housing. Click on each thumbnail or the next button to see each individual picture. You may also click on the magnifying glass to see a larger view of each one. Clicking again on the picture will exit the magnification view.
Incident response. As mentioned previously, hazardous battery incidents are the result of leaks and explosions. The primary hazards after a leak or explosion are the corrosive and toxic atmosphere. When exposed to moisture, thionyl chloride electrolyte forms HCl, which is very corrosive, and sulfur dioxide, which is very toxic to humans. HCl will corrode electronics and exposed metal surfaces. As seen in previous slides, HCl will attack and corrode stainless steel. Sulfur dioxide attacks the mucus in airways and lungs, causing breathing difficulties. If extremely large amounts of sulfur dioxide is inhaled, pulmonary edema can occur, which can result in death. Procedure to handle incident. Thionyl chloride has a very sharp, pungent odor. There is a common misconception that the smell has a rotten egg type odor. This is not true. The odor is more like an extremely potent smelling salt. The first reaction for anybody exposed to thionyl chloride odor is to get away, and this should be the first action. Evacuate all personnel. Ventilate the area until odor is no longer present. By opening doors and using industrial fans, the odor will eventually dissipate. When cleaning the area or removing leaking cells, personal protective equipment such as an acid gas respirator and protective clothing consisting of eye goggles, chemical apron, and nitrile gloves should be worn. Contact with electrolyte. If electrolyte gets into eyes, the pain will be very high and immediate medical attention is required. The patient will need to have his eyes flushed with a saline solution. If fumes are inhaled and breathing problems are noticed, then medical attention should be given. Small areas of contact with skin can be treated by washing with soap and water. As mentioned previously, a battery explosion may result in shrapnel, and if an injury occurs, appropriate medical attention should be given. Procedure to handle hot cell. If a hot cell or battery is detected, immediately evacuate all personnel. If a short circuit causing the hot battery is immediately noticed, remove the short, but don't waste time doing it. It is important to get away from the battery. The battery, if it does not explode, will consume its energy within hours, so wait for the battery to cool completely before approaching battery. This may take as long as 24 hours. All personnel should stay away from the battery during that time. Some facilities will have a battery hot cell container, and if the battery can be placed in this container immediately, do this quickly. If not, get away from the battery as fast as possible. Disposal of pack after leak or explosion. When all components are cool, remove the cell or battery from the area by placing it into a plastic bag filled completely with baking soda. Then place the bag into a second plastic bag. The battery or cell can then be disposed of through normal channels. To clean up the area where the cell or battery leaked, use water and baking soda. The baking soda will neutralize the thionyl chloride. Heating batteries. It is dangerous to apply external heat sources to batteries. Do not apply external heat sources due to risk of explosion, injury, or death. Due to the unreliability, imprecision, and failure potential of most commercially available heating devices, the use of an added external heat source poses a very real risk of personal injury or death to persons in the vicinity of a battery being heated. Depassivation warning. Depassivation of lithium batteries is a complex subject, and it is not covered in this presentation. For safety reasons, the following guidelines are given. Batteries are not required to be heated with external heat sources in order to effectively depassivate batteries. Depassivate using resistance loading only. Battery may be placed in warm sunlight or in a warm room. Do not expose to any heat source other than ambient heat. Depassivation techniques can vary significantly with the user. Excell will work with each customer's unique situation on a case-by-case basis. Storage of batteries. It is important to not let storage conditions cause physical damage to batteries or cause performance problems with batteries. As a result, the following recommendations are given. Use original shipping containers if possible. Store in cool, air-conditioned environment. Care should be taken to not drop batteries. Never disassemble batteries. When checking voltage, ensure short-circuit conditions are avoided. Regulations concerning lithium batteries. Users of lithium batteries must be aware of 3 general sets of regulations. 1. Transportation. The U.S. DOT in the United States and Transport Canada in Canada offer many rules and regulations concerning the shipment of lithium batteries. Users must follow these rules very closely or risk substantial fines due to non-compliance. Shippers of lithium batteries must be trained in the regulations and procedures for shipping dangerous goods. 2. OSHA status. Lithium batteries are considered an article and thionyl chloride is considered hazardous. Thus, employees must receive the appropriate hazard communication training as outlined in OSHA's regulations. 3. Accidental release measures. Follow North American Emergency Response Guide, NAERG, number 138, for cells involved in an accident, cells that have vented or have exploded. A word about Class D extinguishers. Many companies require that Class D fire extinguishers be present in areas containing lithium batteries. While effective for fighting a metallic lithium fire, it is not likely to be effective with cell or batteries that have exploded. A Class D extinguisher may give a false sense of security to users. It is equally, if not more important, to have other fire extinguishers present to extinguish whatever type fire might occur in the lithium battery storage area. Class D fire extinguishers should only be used to fight lithium fires. It is very unlikely that lithium fire will be present even after cell explosion. Do not use Class D on other types of fires that may be present around a battery. It is very important that ABC extinguishers be available to fight fires near battery storage. You are now ready for the Lithium Battery Safety Quiz. You will receive 15 questions to check your understanding of this training. You will need to score at least 70%, 11 correct answers, in order to pass this quiz. Click Next when you are ready to begin.